So the reason it's so important to compose models is that the models that get actually used in the real world are immensely complex. So here's a picture of Osgood and Lee's COVID model. This is a page in AnyLogic, the software. This is the whole model. As you can see, it's an enormous web of stocks and flows and such. And you really would prefer actually not to have to deal with this whole entity at once. You prefer to have it be thought of as being made up out of smaller pieces, because mentally it is made up out of smaller pieces. But that's not captured by the software, unfortunately. AnyLogic just doesn't do that for you. So we've now created software that does that. It supports compositional modeling with these stock flow diagrams. So it's called stock flow. And if you click on this link, you'll go to GitHub, which is where computer programmers keep their open source software. So you can download the software. And so it lets you create and compose open stock flow diagrams and lets you stratify them, that is, subdivide stocks into smaller stocks. For those of you who like category theory, I'll mention that that's done using a technique called pullbacks in category theory. It lets you choose among several different semantics functors, so one of which is the differential equation semantics. And of course, it lets you solve the differential equations once you get them. And then Nate Osgood and another student of his, Eric Redekop, went further and made a graphical user interface for stock flow. So stock flow was written in this programming language called algebraic Julia. To interact with it, you needed to know algebraic Julia. But this graphical user interface called Model Collab, it runs on a browser, and you manipulate the model by actually dragging and dropping little boxes and drawing little edges between boxes. So, and because it runs on multiple browsers, teams of different people located in different locations can collaborate to build stock flow diagrams. So I could build my piece, you could build your piece, we could both save them. They'd be saved on the cloud. I see there's this little thing called cloud here. Oh, that's not what it's actually for, though. Sorry, that's a mistake. But you can save. Nate's gonna laugh at that. Actually, clouds are these little funny things here. But you can save your models on the internet, and so that other people in different locations can access them and then glue them together to form larger models. So in the goal to really apply mathematics, there are many levels, because the next step is to actually train epidemiologists to use Model Collab. So we have some things going for us. So first of all, Nate Osgood runs regular training sessions, which goes by the quasi-militaristic terminology favored in computer science of boot camps, because they're supposed to be intense. So he runs boot camps on epidemiological modeling. So he is beginning to teach people Model Collab. Second, no understanding of category theory or the programming language Julia is required to use Model Collab. So it's really crucial when you're applying category theory that you can ultimately black box the category theory, and so that people do not explicitly need to know it to use what you're creating, although they may be using it in some kind of implicit way. And third, it's free, while AnyLogic you have to pay for, which should ultimately be an advantage. But I should still say it will take a lot of work, because when you have a generation of modelers trained to use AnyLogic, this new paradigm is not so easy to shake. So as I just already said, applying mathematics takes many steps. And as I've moved from being more of a pure mathematician towards a bit more, at least some days of the week, of an applied mathematician, I realize how easy pure mathematicians have it. You just write a paper, you explain your idea, you throw it out there, and you hope that somebody reads it. But when you're trying to actually carry out the full application of an idea, you have to interact with many people with many skills, persuade many different communities that what you're doing is actually worth doing. And it's a much more elaborate, but I should also say very satisfying endeavor. So I'll conclude by saying that applied category theory is interesting in many ways, some of which I hope will be interesting to philosophers. So some of these ways are separate from sort of the core mathematical ideas. So one thing, as I hope I've illustrated here, by my somewhat self-centered history, is that it requires new forms of communication and collaboration because you're talking to new types of people. And luckily, these are starting to come into existence. So there's an annual applied category theory conference that's first started in 2018, run that time by Brendan Fong and some of his other young friends. Another is a journal. So there's a journal called Compositionality, which is again started by Brendan Fong and some of his young collaborators and friends. This is an open access, free to publish, free to read journal of applied category theory, which I recommend to your attention. And another is called the Category Theory Community Server, which is sort of like a chat site or a discussion site for applied category theory, actually for all category theory, but it has a lot of applied category theorists there. This was initiated by my grad student, Christian Williams. And so these are different ways for category theorists to start talking to other kinds of people, people who might want to apply category theory or learn category theory. And I hope that these catalyze the process that I'm trying to outline here. Another thing is that category theory raises ethical issues in ways that category theorists aren't used to. Pure mathematicians tend to feel themselves somewhat insulated from a lot of ethical issues because although their math may get used for all sorts of purposes, they don't consider themselves particularly responsible for how their mathematics gets used because it's so abstract that they sort of can blame someone else for understanding it and doing something with it. But when you start doing explicitly applied category theory, that sort of veil of protection is ripped open, and you see that what you're doing may have a fairly immediate effect. So, for example, the biggest funder of research on applied category theory is currently the US military right now. And also, a lot of applied category theory is being used for artificial intelligence or machine learning or large language models or so on. So I'm not saying that those are necessarily bad things. I'm saying that those are things that definitely raise serious ethical issues. And so I'm worried about the danger that applied category theory will wind up merely intensifying the already existing patterns in society. That is, it will only make the richest and most powerful people even richer and more powerful. I would prefer it if applied category theory could do something really different, really new. This is one reason why I've tried to focus on epidemiology, which is a little bit different than some of the other applications. Of course, even epidemiology ultimately feeds into the healthcare system, so there are questions about that as well. I would really like to use applied category theory for environmental issues, but I haven't quite gotten there yet. Anyway, I just wanted to emphasize that ethics is the provenance of philosophers, and this is a really interesting intersection of mathematics and ethics, which I hope that people think about. And another thing applied category theory does is revitalize what is a very old question: which mathematical structures are best for describing and designing systems? I emphasize designing because with the rise of computers, whatever you can think about clearly enough, you can make. So it's not merely describing the external world, you're also making worlds based on your descriptions. And so with this immense freedom that you have in computer science, the question is what should guide you? And it opens possibilities for some really radical progress, because these are some really brand new ideas that we're talking about here that may let us organize systems in new ways. So I think there's a lot to think about here, and I hope some people here give it a try. Yeah, the question of static versus dynamic is, as you know very well, a extremely tricky question, because I could take any dynamical system and when it's done, or when we imagine it as being laid out in time, then we can think of it as a static thing, with time as just another space-like dimension. And I think it's very hard to like definitively break out of that. But nonetheless, category theory is a generalization of set theory, in a sense in which, instead of just having elements in a set, you have objects and also morphisms, and the morphisms are meant to convey some kind of dynamic aspect of the system. That is, a morphism goes from an object to an object, and that's a very primitive sense of dynamics there, of the start and the end, and it brings a kind of dynamical quality to the foundations of mathematics, which is a real thing. It's not just an illusion. I mean, even though if you ask a traditional mathematician, what is a category, and they're saying, oh, it's a set of objects and a set of morphisms and some functions doing this and that, right? So you could say, oh, we're just back in the same old paradigm. And that's what I meant by it's hard to definitively break out of that paradigm. I think it's more, in some ways, more of a question of attitude rather than anything else. And anyway, I think the interesting thing about the differential equations here, the interesting new thing, maybe the study of open differential equations, which are differential equations where some quantities are explicitly labeled as affected by the outside world, affected by the part of the world which is not modeled by the differential equation. So traditional differential equations, well, no, physicists often like to study what are called autonomous systems of differential equations, where you know everything there is to know once you know the differential equations. Whereas open differential equations, which I should say are also studied by physicists and especially engineers, have certain quantities which are not determined by the differential equation. They're regarded as being affected by the outside world. And that on the one hand allows you to treat systems of differential equations as morphisms that you could stick together by sticking some of these quantities on the edge to some other quantities on the edge. But it also means that you're not just dealing with a deterministic system in the classic sense anymore, because you have quantities that are affected by the unknown. So it definitely changes your attitude towards differential equations. The algebraic Julia community is really trying to blend computer programming with category theory in a really rich way, so that you can write software and you can say, define functor, blah, 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 define pre-sheaf category, blah, blah, blah. So that's just one of several different initiatives to try to bring category theory into programming. So not just have it help programming it, but have it actually be part of the programming. So that's one thing. There are lots of other things, and I probably don't know a lot of the other things. So I will just mention again this company, Connexus.ai, uses categorical approach to databases. So it turns out that updating databases is very nicely described using categorical ideas like on extensions. And Mike Johnson in Australia has been serving as a consultant for database companies using category theory ideas for many years. But now this company, based on David Spivak's work, is also doing that. And there are a lot of other things. I should say that there's just a lot more on the computer science side that I'm not very familiar with.
Okay, so well, here we've reached time. So what we have to do is thank John very much for his very interesting talk.
Thanks.